Can you all hear me?
Yeah.
And I hope I speak clearly enough as well. I have to start really genuinely thanking you very much, Professor Yamamoto, for inviting us. It's a real honour to be part of this symposium and also to take part in the TFC activity. When we understood what you're doing here with the Megabank, me and my good colleagues from KI Biobank, Tuva Rilanda and James Thompson, we were very impressed with what you're doing. So it's a real pleasure to take part in this and to be part of an ongoing discussion and dialogue with you, and hopefully even a collaboration. That would be great. I also want to live up to your very well made comment, Professor Yamamoto, on keeping the time. So I've even brought with me a little alarm clock here. I'm going to start it now. Maybe I should take off a minute for what I've said already, but it's going to ring in 39 minutes time. And if you get bored of me before then, you can kick me off the stage already. Let me take you through the journey that we've gone through in Sweden, or a little bit of it, with setting up biobanks and using them to try and improve public health and improve healthcare. We've learned a lot of lessons on that journey, and I'd say we've got a lot more lessons to learn. And if we can learn some more of them from your experiences as well, that would be great for us. Liam, your comments or your quotation from Watson, I really took home. This business about effective criticism, it's very much part of making things better and learning. The world we come from, James, Tuva and I, it's full of effective criticism. Regrettably, it's also full of some negative criticism as well, so we're used to that. It's been a rich part of our life, and it's part of our ongoing continuous improvement. Biobanks, as I'm sure everybody in this room knows, have been with us for a long time. They just haven't been called biobanks in the past. For at least 100 years, people have been collecting samples from the natural world, from the human world, to try and help understand what goes wrong. It's part of that learning process again. Collect samples from patients suffering from different diseases, and you have a good material to start trying to understand what the problem is. And it's only through understanding the problem that you have any chance of coming up with some good solutions. This whole activity that we call biobanking today has progressed enormously in the last 100 years, so that within the last 10 years, people have been collecting human samples in an organized, systematic way, the way that today we call biobanks, to the extent that we're now looking at millions of samples that people are collecting to do medical research. I think it's great that the name of the new biobank here is called the Megabank. That's a very good reflection of the scale that you need to do this kind of work. And modern biobanking has really come a long way in that 100-year period. In fact, just simply the last 5 years, the technology impact has been enormous. We have data collection systems, we have analysis methodologies, we have logistics systems that mean that we can handle ever-increasing numbers of samples. For me, originally my background was in molecular biology and microbiology. I grew up in a molecular biology world in the 80s where we were extremely proud of being able to look at one single molecule and pick it apart and break it down into its component pieces, whether they're amino acids or nucleic acid structures. The thing that I completely overlooked when I was a PhD student 20 or 30 years ago was the fact that without statistics, those conclusions you draw from looking at single molecules usually often can mislead you. And the power of modern biobanking is that power of using statistics much more effectively. And I think it's that's led biobanking in the last few years to become what's now frequently called an essential tool in translational medicine. being able to convert the knowledge we win from the lab into some kind of benefit in the clinic, and also being able to use clinical experience, if it comes in the form of human material, to enrich the way we do our lab research. That's where we get the benefit. And now what we're doing in modern biobanking is starting to look at, if not whole populations, very significant portions of populations. And it's now very common when you go around the world to find different countries initiating their own version of a population cohort. Among the most well established is the population cohort in Norway that's become known as the Hunt Biobank. That's actually one of the oldest modern biobanks, I would contend. And it's been extremely successful in enriching medical research in Norway, and they're also reaping the benefit of impact on healthcare already. Another one that's known very well because of its sheer scale and ambitiousness is the UK Biobank, an extremely exciting, extremely impressive undertaking, and that's pushing on with a vengeance. It's always impressive to hear an update from UK Biobank, and I'm sure many of you know about it already. And we can find many more examples. In Sweden, we kicked off a cohort that is similar in its ambitions to UK Biobank. It's called LifeGene, and you'll hear a little bit more about that from my colleague Tove shortly. And there are many other cohorts. And if you think about the net effect of these, it's millions of individuals we're looking at around the world. And we're all individuals, we all have quite significant differences, as well as the many common universal things that keep us together. But those differences means that when we're looking at the scale of millions, the statistics becomes more convincing. Let me start to talk about the experience and the reflections we can get from Scandinavian biobanking. Scandinavian biobanking has been in the news quite a lot the last few years. It's often described as the Scandinavian gold mine. It's this combination of a few rather powerful, what shall I say, advantages that you find in many of the Scandinavian countries. There has been a history of collecting human materials in a systematic way for many, many years. In healthcare in Scandinavia, it's very common to keep registers on the effect, on the quality of healthcare strategies. There's usually a healthcare register for most disease areas, and they're very good catalogues of information. Another thing that's been very valuable in the Scandinavian context has been the fact that the general public are often supportive to medical research, and if not supportive, they're at least not negative. Whereas in many other countries, the country I come from originally, the UK, that level of public support doesn't exist. When UK Biobank started, if you looked on the internet, you could find many, many examples of the kind of conspiracy theory that floats around biobanks. That a biobank is there to collect material for the police, so that Big Brother can watch us and correct us if we're not behaving well. That kind of conspiracy theory meant that in the UK, people were very, very suspicious about UK Biobank. In fact, you can still find a little bit of skepticism. In Scandinavia, that skepticism almost never occurs. People donate their samples with a lot of trust. We have a very good level of trust in the Swedish society. My impression of the Japanese society is it's similar. And that's a trust we have to keep with us by making sure that in our biobanking activities we do them with a very high ethical standard. The fourth jewel in the Scandinavian gold mine is the fact that we have a personal number system. Every individual has a unique number identifier. That means from a statistical point of view, the tracking of data is very easy. People talk about the Scandinavian gold mine very frequently as though it's a guarantee that you're just going to be successful in biobanking. That's not the case. Sweden, like every other country in the world, has its challenges to cope with, and sometimes those jewels in the gold mine are buried quite deep. Even though we have a high trust level in Swedish society, it is a complex landscape of laws and ethical regulations. Our infrastructure is often fragmented, even though people talk openly about collaboration. Real collaboration is sometimes a different thing and demands more willingness from individuals than people expect. And biobanking is one of those areas that's quite often burdened by worries or arguments about ownership. Who owns the samples? Is it the donor? Is it the principal investigator who puts the idea together? Is it the hospital or is it the state? Those arguments, even though in fact the legal guidelines are fairly clear, those arguments still cause us loss of time because of arguments and disagreements about who has the rights over what. And all these systems, whatever we do in our societies, it usually has some element of bureaucracy in it. So it means that you can spend a lot of time digging for the jewels, but you don't always find them quickly. The biobank landscape of Sweden has many different biobanks. We even have a register for the biobanks, and in that register there's now over 1,000 biobanks registered. In reality, there's probably about 600 real physical biobanks, and in fact we use the term biobank frequently just simply as synonymous with a sample collection. In reality, a biobank is a little bit more than just a sample collection. In the healthcare environment, in the hospitals in Sweden, there are many millions of samples, and that's not at all surprising, of many different types. The problem in the healthcare system is they're not always very well organized, not always very accessible. And the university system in Sweden has done a better job of systematically tracking its sample collections to make them more accessible. In the university systems we have less samples, but as I say, they're more accessible. Sweden took a fairly brave initiative 6 years ago in a decision at the top level, the Swedish Research Council, to devote a lot of funding, 170 million Swedish crowns, to improving physical biobanking in Sweden, to try and overcome some of these problem areas that I talked about, to overcome the bureaucracy, to overcome the poor accessibility to samples. And we've been working on that concept for the last 5 years. My colleagues Tuva and James are going to show you some of the effects of that. And in Sweden that's now become a reality. I would like to claim that that's made some good progress. One of the things we've done is introduce more modern technology to biobanking. Sample collection is often done or has been done in rather old-fashioned systems that don't lend themselves well to modern automation and modern data systems. We took the chance with this initiative and this investment to introduce modern technology that, I call it modern, it's been around for quite a long time. It's mostly been the pharmaceutical industry that's used it in drug discovery, but it's super technology. It's wonderful in the academic research lab because you can automate, you can track things in a very reliable way. And we use microtiter systems where each individual sample has a unique two-dimensional barcode that's instantly trackable. You can trace them in your mobile phone now with modern scanners. And it means that all our systems are linked up into a single data system. Theoretically, we could access it from here and start to identify samples we want to access. It means our systems are more effective, even though it costs a lot to install them and still costs a lot in time to improve them. They're a hell of a lot more effective than the old-fashioned systems with cryotubes and old-fashioned test tubes. That effectivity it's given us, it actually automatically gives you a higher quality. Everything is treated in the same way. And in time it'll give us a lower cost, and it gives us a much more stable basis for improving things systematically and successively over time. And now in Sweden, through this initiative called BBMRI.se, which is the BBMRI initiative of Sweden, we've systematically started assembling a whole series of cohorts. Some of them are historical cohorts that we simply reformatted into the modern format. Others of them are new, like the life gene cohort that you'll hear a bit more about a little bit later. We have cohorts that are dedicated to specific disease areas like breast cancer or prostate cancer, cardiovascular disease. And even more exciting, we have smaller cohorts that are dedicated in a more specific way to detailed diseases with material from patients. And there's a whole list of them. I don't want to spend time going through all the list. The neat thing with our initiative is that by introducing this new technology in a standard way, it's given us almost automatically a harmonization or a standard format, so that samples and data are interchangeable between these different cohorts, and ideally between different universities in Sweden, and if we get it right in the European initiative, even between Europe. In our Swedish initiative, we've spent some effort on how we share the learning, share the protocols, share the analysis technologies, and we've set up websites where you can access data on different analysis technologies, platforms like genomics and proteomics. Please take the opportunity to go in and look at these websites. You'll find them under the BBMRI.se website, and of course you can have this material afterwards. You'll find quite a lot of material there. You'll find contacts to different analysis technologies. Of course, we've started this in Sweden, so most of them are Swedish, but we're extending it to European countries, so the span is increasing. We would love to extend it more internationally, and this may be an area where we could have some collaboration just at a very simple level. And you can go in and delve down and find details about more of those technologies. In a similar way, we've established a website for protocols. Sounds a little bit boring, but if you think about the net effect of sharing protocols, you get almost into the bargain over time more and more standardization and harmonization, which makes the data more relevant. And really what I wanted to talk most about in my talk is the impact of this kind of technology and this kind of more systematic approach. And the best way to talk about impact is by showing examples. And because Karolinska Institute's Biobank has been running now for 10 years, we're starting to see some of the benefit of those examples. And there's some really nice examples. We're seeing benefits. Probably the first one you can see the big benefit from is from the Swedish twin collection. The Swedish twin registry has been a long-running systematic data collection for a long time, since the last 50 or 60 years. First making use of church records, was set up by two very forward-thinking Swedish people, Lars Friberg and Rune Cederlöf. And up to now, they've identified 200,000 Swedish twins that exist in this register. And Zygost has been assigned for 150,000 of them. And now we've collected lifestyle data for many of them. We have health control data. There are the healthcare quality registers and some testing information. A lot of testing on cognition, how these Swedish twins perform in different cognition tests. And now, with the last few years' progress in analysis technologies, we're starting to build up biochemical databases. We have a DNA bank from these twins, and we're starting to do genotyping and other analyses. It's a powerful biobank, and it's led to some really nice science. It's just a snapshot of the science. I hope you in the back row can read the small print there. I think even you in the front row can't read the small print. My wife said this was the worst PowerPoint picture she ever saw. She's right. It was really just to give you a flavour of the fact that the Swedish twin collection has been the birthplace of a lot of exciting science. As I said, lots of it has been in psychiatric disorders, and we get publication after publication in high-impact journals looking at the interplay between genes and environment in some of these complex disorders that are not very well met by modern therapies. For me, my favourite success story from KI Biobank is one related to multiple sclerosis. Multiple sclerosis is a disease that I think here in Japan and other Asian countries is not very well known. It turns out to be a typically Scandinavian disease. 17,000 cases in Sweden. That's 10 times higher than in Germany, which has a much bigger population. We now have many of them represented in KI's Biobank, and the researchers behind that, Thomas Olsen and Jan Hillets, they've been very, very successful in their research. They're leaders in the field, and together with some of the drug companies, they've helped in the development of new drugs for MS. MS, as I expect many people know, is not a very easily treated disease. One treatment that came out nearly 10 years ago, a monoclonal antibody called Tisabri, looked like it was going to be very, very successful. Groundbreaking treatment in a disease that's very poorly treated. It looked like it was very effective. It was certainly very expensive, a typical monoclonal antibody drug with a very high price tag for the healthcare. During the clinical trials, it hit some very serious side effects, the kind of side effects that kill most drug development programs. In some cases, there were patients who died. Turned out to be a very unfortunate cross-reaction between the monoclonal antibody and a virus that 50% of us carry with us. I'm not sure whether that frequency is the same in a Japanese population, but in a Swedish population, 50% of people carry this polyoma virus. It sits in our kidneys. And it has nothing to do with MS, apparently. But unfortunately, the drug cross-reacted with it and had this, in some cases, lethal effect. And that effect was promising to kill the drug, a drug that looked very promising for some patients. Simply by screening the biobank we hold for that virus, you could, in one sweep, identify the patients who were at high risk of having a serious, if not lethal, side effect from those who had no side effect and everything to win from taking a very expensive drug. That was a fabulous example of personalized medicine, where you match a really promising drug to the right patients. And it really was a classic win-win story. The drug company, which was a fairly small biotech company, faced losing everything on an unsuccessful phase 3 program. But because of this discovery exploited by these Swedish researchers, the whole story was turned around. They got an FDA approval to license this widely, and it's made their prospects look a lot better. The most important thing is the prospects for the patients are a lot better. And there we see a good example of where I see the real value in biobanks. The value is in improving clinical practice. We have better screening or diagnostics and a better choice of treatments. If you think about that on a population scale, if it's a large disease with affecting many individuals, there's a huge amount for society to win by treating it in this systematic way. Even if it's a small disease like MS, if the treatment is expensive, there's also a significant health economic value to be had out of that. If you think about that last example I gave you, there was a nighttime to daytime improvement in the prospects for drug development. And that's one very powerful example. There are many more. If you think about human papillomavirus vaccine as a drug, which is maybe a broad definition of a drug, that's also, what should we call it, a transformative impact. And that vaccine was only brought about by the use of biobanks in understanding the role of human papillomavirus in cervical cancer. The fourth value that I identify in this kind of biobank-based research is not so easy to define as health economic value is. It's that ethical credibility. But in situations where the public may have a reason to doubt what we're doing with biobanks, and sometimes they may have a genuine reason to do that, it's very, very valuable to be able to point to these good examples and help people understand that this is not an activity about controlling people or cloning people or inviting the police to come and look at our private lives. It's something that is really benefiting individuals and society. And that ethical credibility is very important. Even in Sweden, that has, as I said before, this very high level of trust in society. Early on in our life gene cohort, we ran into big trouble with the Swedish data inspection, who believed that the life gene study was illegal. The fact that it's associated with this kind of high value, high society value thing, I think was maybe one aspect in the fact that we managed to solve that problem. And I think Tuva will talk a little bit more about that later. According to my stopwatch here, Professor Yamamoto, I still have a little bit of time left. Very good. I think I'm going to come in on time, for those of you who are wondering. Very good, thank you. The gradually accumulated experience of these kinds of efforts has helped us in our biobank in KI recognize that there's a really big value in the in-depth detail that small sample collections in dedicated disease areas, often in small disease areas, the learning from that combined with the learning and the technological power of the really big cohorts, trying to look at hundreds of thousands of individuals. If you combine those, it's our belief that you'll get a much quicker impact on public health than you would do before. And if we look at some of those really common disease areas, like cancers, whether it's prostate cancer or breast cancer, diseases that affect up to 10% of the population, cardiovascular disease as well, the impact there should be much, much bigger if we can harness it. And that's what we believe we're starting to get a handle on in some of the cohorts that we're running now. And I want to highlight one example. My friend and colleague James is going to highlight another example a little bit later this afternoon. The example I want to bring up is a cohort we have around breast cancer. This is a prospective cohort, so it's not looking at patients, it's looking at women, many, many women. It's 70,000 women now in Sweden have been induced into this cohort, so that most of them hopefully are healthy, although since it's been running, some of them have succumbed to breast cancer. It'll be around about 10%, as I say. It's been running for about 2 years, and it invites women who come into routine mammography screening at the age of 45 in Sweden, simply to take part in the study. And they do it with informed consent. It's done in following all the legal and ethical guidelines. And the interesting thing is, it's a very high response rate. Most women, when they get told about it, want to be part of it, and they don't want to leave it once they're part of it. They give a blood sample that comes into our biobank. They fill in a health survey on the web, which is fairly easy for them to fill in even though it includes hundreds of questions. They're all very dedicated to filling it in very thoroughly, and it asks quite searching questions about their lifestyle as well as their health status. The kind of data all of us, I think, would consider highly personal, but they're willing to give it to research. It gets anonymized, and we treat it with very high integrity, and they trust us to do that. They also trust us to take care of their mammography data, the images that are taken of their breasts when they come in for the screening. And that combination of the physical sample, the mammography data, and the lifestyle data is already very powerful. Through this study, we've extracted all the DNA from all 70,000 women, and this has been done in less than a year and a half. So we have 70,000 DNA samples that already have been primarily screened in some kind of genetic analysis. And through that, they've been able to identify at least 50 more genetic associations with breast cancer. You can say, so what? There's SNPs being identified all the time. But in the context of this study that is taking a very wide statistical sweep, that fairly pedestrian result, I think, promises to be very powerful. Seen in the light of the fact that with 70, now it's close to 1 million different breast images they have, they can start to identify trends in that phenotypic data and associate, for example, breast density with risk for breast cancer. You put that alongside the genetic data and the idea of risk associated with different genotypes, alongside risk factors you identify from the breast cancer images, risk factors from lifestyle questions, whether it be simple things like smoking or other lifestyle factors. The belief of this researcher, Per Hall, is that it should have an impact on breast cancer treatment strategies within a few years. And he's now moving on to a really powerful clinical study based on the data they've got on risk prediction. With some kind of prediction of risk, you can take the next step and ask what a good prophylactic therapy might be, and that's what he's going to test in his next step. That was actually the conclusion of my talk. I can't conclude without thanking all the people who lie behind all this work. Of course, it's the staff of Karolinska Institutet Biobank. There's just 3 of us here today. Back in the lab, there's 30 of us. And our colleagues in the whole BBMRI initiative of Sweden have also done a hell of a lot to put this together. But in fact, it's the researchers who've had the ideas for the studies, who've designed the studies, and had the energy and won the financing to do the studies that have meant that the biobank has been filled with valuable material. And it's those people I want to thank when I give these acknowledgements. And leave you with our view of a health warning about biobanks. Biobanks are very good for health. Thank you.